All over the world. This is another edition of STEM Communication, an online schooling and coaching program for all categories of students. This is another aspect of, we are looking at another aspect of STEM, which is physics, and we want to continue with the series on dimensional analysis, part 5B. We have done that to part 5A. The reason for this part A, B, and even that to part C is because of the diversity of questions that can arise in an area of importance or application of dimensional analysis, which is establishing connectivity in formula or equation of physical quantities. How are the physical quantities, the variables that make up an equation or formula, how are they homogeneous, how are they compatible, and how are they correct or related? So there are some questions that are a bit more trickish than the one we did under part 5A of this dimensional analysis. So I have some questions on the board for us to practice. I will just do problem one, then I will leave problem 2 and problem 3 for you to practice at home, even though I'm going to explain it. Now let's look at problem 2. I'm going to do problem 1 and done with the communication in just a few minutes now. Now, problem 2, I'll just explain to you so that it will be easier for you to handle it after you might have seen me attempt this. The frequency of vibration. The frequency of vibration. Look at the symbol they use for that, to observe frequency. Instead of F, they use this symbol. Of a string of length L having mass per unit length kept under tension, that F, that is a force, is given by, look at that is frequency of vibration, equals to 1 over 2L square root of force over mass. Check the correctness of the relation. At the end of the day, by the time you subject this to dimensional analysis, whatever physical dimension you have at the left hand side must definitely be the same thing as the one you have at the right hand side. So take note that this is frequency. Frequency is per second. So that is 1 over T. This is L, the dimension is capital letter L. You have to split this force down into mass times acceleration. Mass is capital letter M. Acceleration inside this force is capital letter N over T, capital letter T raised to power 2. Then this is also under mass. Now the problem you'll be having with this is that you have to remove this square root. Remember, I have always been saying that anything that is inside square root symbol is like bondage. It's like something is inside bondage, it's like something is in prison. And the only way you can remove this is to square both sides. If you square both sides, this will be frequency raised to power 2. That means it will now be 1 over T squared. This will turn to 1 over 4L squared. Then this one, the square root symbol will disappear. And with that, make attempt to check the correctness of the relation. The third one that I also want you to practice is the rate of liquid. Listen to that. The rate of liquid flow. Now, anytime you hear anything rate in physics, it means something over time. In this case, they are talking about liquid. Liquid is measured in volume. It means that rate is volume. That rate actually means volume over time. If I say rate of distance, that is speed. It means distance over time. If I say rate of displacement, that is velocity. It means displacement over time. If I say rate of velocity, that is acceleration. It means velocity over time. I hope you get that. So please take note of that. It's a very important interpretation that you need to know in science anytime you mention rate. So it said the rate of liquid flow with a coefficient of viscosity. This symbol looks like the one they use for frequency here, but this is the actual symbol for coefficient of viscosity. Through a capillary tube of length L and radius A. Can you see that? Instead of using R, we use A for radius. Under pressure H. Pressure H means pressure, okay? P is given by, you see that? Now look at this. This is the rate. And now I told you the other time that any time they mention the rate, it means the volume over time. This V now does not mean velocity, it means volume. Okay, because liquid is measured in volume. The quantification of anything liquid is in volume. So dV dt. If you remember that this dV means L raised to the power T, L raised to the power 3, L cube. Dt means time, capital letter T. Now, this is pressure. Pressure is force over area. You have to break that force into mass times acceleration, and you break it down into physical dimension. This is radius A, that is R. Radius is length, L raised to the power 4. Then this one is pi and 8 will disappear. You don't need your dimension analysis. Okay, this is length. Then this is the coefficient of viscosity. Now, if you look at this coefficient of viscosity, there is a formula for it. Look at the hint here. Coefficient of viscosity, okay, is force divided by area times velocity gradient. I take that again. Coefficient of viscosity, okay, look at the symbol, equals to force divided by area times velocity gradient. Now, that's another time to explain. When you say velocity gradient, if I say velocity gradient, what does it mean? It means velocity. It means change in velocity, dV, per unit length. Take note of that. If I say velocity gradient, what it means is that velocity per length, velocity, change in velocity over change in what? Length, dx. Okay? So velocity is L over T, dx is L. So you got the clue there. Though we are going to explain this in detail now. Now, if I say temperature gradient, it's another thing you need to know. If I say temperature gradient, it means change in temperature over change in length or x. So gradient, it can be velocity gradient, it can be temperature gradient. So in this case, we are talking about velocity gradient. So coefficient of viscosity, it appears in this formula. So we need to get the dimension of this. Now, in the problem that I want to solve here, if you look up here, there's also coefficient of viscosity appearing in this formula. So because of that, before I go into this, let me quickly solve this first. Let me find the let us write out the dimension of this coefficient of viscosity based on what I've just explained. So I'll be doing that right here now. Okay. Now we are told that this coefficient of viscosity is force, which is mass. Okay. Mass times acceleration, okay, divided by area, that's capital letter A. Then velocity gradient, like I told you, it means change in velocity per change in distance, okay, or length. Now, dimensionally now, mass is capital letter M, acceleration is L over T raised to the power 2. This line means divided by, so I'll put it here, divided by, you see that? What? Divided by what? We have area, which is L squared, dot velocity, which is L divided by T. Then ds, another divided by L here. Can you see that? Ds means length. Now, let me write it properly here. This is M L over T squared. Okay? If I change this division to times, all these things that are at the denominator, L and T, will go up. So I have L dot T divided by the one at the numerator, L squared times L will come down. L squared times another L. Now, this is M L over T squared. Are you following? Equals, times, this is LT divided by, this one will have 3L at the denominator, that will L raised to the power 3. Now let's try to see if this thing can cancel each other. At the numerator, we only have only one mass, capital letter M, so we'll put one M. We have 2L at the numerator, one L times L times L, that will L squared. We have 3 at the denominator, so if it cancels, it will remain 1 down here. Then at the numerator we have 1t, and at the numerator 1t, denominator we have 2t. It will cancel, it will remain 1 down here. Now, this is equal to, I want to take everything up. That is m. If I take this L up, the exponent is 1. That will be L per L. If I take this T up, it will become per T. So it means dimensionally, this coefficient of viscosity is m per length per time. Now, I want to now go ahead to solve this problem 1. But before then, I want you to look at this question properly, take note of it because I want to rub it off. I don't need this again. I expected you to have taken note of this. So I want the camera to be focused on that so that our audience and can see those questions there. Okay? Now, I'm free to rub it off now so that I can be able to solve this problem number 1. Once you're able to follow up in the way I'm going to do this, then it will be easier for you to do all those ones. Especially when I've already explained to you what you need to do. So, how to clean this so that I can have space to solve that problem. So we already know the dimension of our coefficient of viscosity. Okay? So let's see. Now let's look at the problem that we have. The problem. It said the terminal velocity V, don't forget velocity, of a small sphere of radius A and density rho falling through a liquid density, another density. You see that? Another density, sigma. And coefficient of viscosity, which we already know the dimension, is given by this. They now ask us, is the relation homogeneous? Meaning, is the equation dimensionally balanced at both the left-hand side and right-hand side? It also means, is the equation viable? Is the equation correct? Is the equation reasonable? Do you understand? So that's what they're asking. Because if it is not reasonable, then there will be an imbalance in the dimension at both the right hand side and left hand side. Now, if you look at the left hand side, velocity, V stands for velocity. It means that the dimension of this V is L per T. That's velocity. It means that by the time we are finished analyzing all this one at the right hand side, you must get L over T. Otherwise, the equation cannot be said to be homogeneous. Do you see that? Okay, so this gives us, let's try to see how that will be. This is 2, I'll put the 2 there, even though it will soon disappear. G is acceleration due to gravity. That is L over T squared, okay? Dot. This A is described as the radius. Can you see that? Of the radius of the sphere. Radius is length. That will be, and it is being squared. So that will be L squared dot. Now there's a bracket here. Now let's look at this bracket closely. If you look at this bracket, the two of them are density, so they are compatible. So it's as good as taking them, this to this. It is this minus this. Okay? It's just like, take note of this. If I say A plus B or A minus B, these two arithmetic operations show sameness. You can only add two things that are dimensionally the same, that are alike. You can add human being with human being. You cannot add human being and goats. It's not compatible. You can add 20 naira with 50 naira. You cannot add 50 naira with $70. They are not compatible except you do conversion. But in this case now, this one is the density of the sphere, and this one is the density of the liquid. So the two of them are density. So I take the two as just density because they are compatible. It's as good as referring to them as just one density. Did you get that? So arguably this is different from this. You dare not do that. It will be a different ballgame entirely. Okay? So do you understand that? So now this one now means density. So I need to put it in bracket again because I already know that density is mass over volume. That is capital letter M divided by M raised to the power 3. That's the unit of volume. Then everything divided by, can you see that? 9. This is 9. Then dot, that is times coefficient of viscosity, which we already know the dimension to be this. Look at it. That's the dimension when we analyze coefficient of viscosity. This is the dimension. So we just put it there. That will be N. Okay? L minus 1. t exponent minus 1. Now, anything that is number that starts as coefficients will disappear. We don't need it. So we have at the left hand side L over T being equals to. Now let's see what we are going to do here. All these ones can come down. It depends on what you want. Okay, let me start with this. This is L raised to power 3. That is L times L squared dot M. Now I want to take this. I'm still dealing with the numerator. Okay, don't forget, I'm still dealing with the numerator of this fraction. I want to take this up. That will be t minus 2 dot. I want to take this up. That will be L minus 3 divided by M L minus 1 t minus 1 exponent. Do you see that? Now I want everything to go up. I don't want anything at the denominator. So left hand side is still L over T. This is equals to, now look here. That will be L raised to power 3 dot M dot T raised to power minus 2 dot L raised to power minus 3. Now I want to take all this up now. This M, if you turn to M raised to power minus 1, because it is 1 before, minus 1. You can see that this, what is there is 1. If you take it up, the sign changes. This one is L raised to power minus 1. That one will change to L raised to power 1. It's not to positive. This T also will go up, there will be T raised to power what? 1. Yes. Everything is now on a straight line. So I can now apply law of indices. By comparing this one, go with this. Do you see that? This M go with this M. Can you see that? Then this T go with this T. Now that means I will have at this side I have L over T equals to, now let's start with that of the M. We have M, L is appearing in 3 places. 1, 2, 3. They have the common base, so I'll add the power. 3 plus minus 3, that's 0. 0 plus 1, that is L. 1, that will be L raised to power 1 dot. Now let's go to that of M. Here is 1. If there is no exponent, it's 1. They have a common base of M, so I can add the power. 1 plus minus 1, that is 0. 1 plus minus 1, that is 0. Okay? Dot. I'll go to the dimension T. T raised to power minus 2 times T raised to power 1. They have a common base. Minus 2 plus 1, that is minus 1. Now, if you look at this, I have at the left hand side L over T being equals to anything raised to power 0 is 1. So this will disappear. This one is 1. It goes off. So what do I have? And anything raised to power 1 is that thing. So this is L dot what? T raised to power minus 1. Can you see that? So what do I have now? I have L over T this side. Or if I like, I can change this one. I can take this up. This T at the left hand side. It will become L T raised to power minus 1. Do you see that? Because what it says is 1. Then equals to L T minus 1. Can you see that it is indeed homogeneous? The relation is homogeneous. Because what I have at the right hand side is what we end up having at the right hand side. Both the left and the right are balanced dimensionally. That's what we mean by homogeneous. The relation is actually homogeneous. Very interesting. So we're looking at the third version of this particular dimensional analysis, 5C, in our subsequent edition, where we establish connectivity in formula or equation of physical quantity using dimensional analysis. That is the fifth importance or advantages or benefits of dimensional analysis in science. Please, I want to encourage you to keep subscribing to this particular educational channel. You share with your friends, neighbors all over the world, and you also support us. If you go through our channel, you will see at the end of this production, you will see a banner showcasing how you can be of help for the continuation of this production. You have to remember that the essence of your living is to be of benefit to another person, and we have created a platform to be of a benefit to humanity. So we sincerely call upon you to come to our aid financially, morally, otherwise. Thank you very much. Keep watching our STEM communication from time to time. Do have a nice time. Bye.
Focus your attention on me. I love them, wanna be your boo, but not me, got you in the mood. Taking every fucking on the island, got your body giving me the ginger, even if not one time, but me, I got you, living like a gangster, let me be beside ya, Ashimola, I love the man, them testify, say me and you, we the company, I love the one to know, I'm on Tosha, my baby, Tashimola, I love the man, them testify. I love the one to know I'm a Tosha, my baby, my baby, yeah. In this villa, me and you, all of them go see us. We they do, we funny, yeah. Bad man no get time for Cassie. Bad girl living high, living fancy. I love them want to jealous me, but they no got you, so I double up on my soda. I love them want to talk, bad girl feeling like ranger, but for you I buckle up, but they do my things, yeah. Ashimola, I love the man, them testify. Say me and you, we the company. I love the one to know I'm a Tosha, my baby, Tashimola. I love the man, them testify. Say me and you, we the company. I love the one to know I'm a Tosha, my baby, Ashimola. Say me and you, we the company. I'm a Tosha.